आइए हम सुने विज्ञान की अनकही कहानियाँ। आइए हम सुने विज्ञान की अनसुनी कहानियाँ। एक नई दुनिया की आवाज़ आपकी आवाज़, विज्ञान की आवाज़, की आवाज़।
We bring you all a podcast series on STEM popularization, that is, science, technology, engineering, mathematics, and medicine, supported and catalyzed by the National Council for Science and Technology Communication, the Government of India. Program is produced by Media for Community Foundation.
Welcome back to the podcast from the Indo French Center for the Promotion of Advanced Research, also popularly called as CEFIPRA. We are dedicated to showcasing the groundbreaking collaborations between Indian and French scientists that are expanding the frontiers of knowledge. Now, let's understand more from our scientist.
I'm Abhishek Dhar, and a professor of physics in the International Center for Theoretical Sciences in Bangalore. So this is the center of the Tata Institute of Fundamental Research, which is based in Mumbai. So I'll talk about this project, CEFIPRA project that we did. This is on understanding large deviation properties of systems of interacting particles, especially in the case where the interactions are long-ranged and very strong interactions. So I'll go on to describe the project. So in this project we actually studied three different set of problems. The first one looks at sort of a problem which is largely motivated by recent experiments on what are called trapped atoms at very cold temperatures. So basically they are very strongly interacting systems which are placed in sort of traps, and some of the interesting questions are how do they thermalize, and what is the equilibrium properties of these strongly interacting systems. So we studied a class of models, it's called the Reed's model, where the interaction, it's a set of particles moving in one dimensions, and the interactions are sort of long ranged and have the form of some power law 1 over r to the power k. So there are lots of interesting questions like thermalization and so on. We looked at a few basic questions. One of them is in equilibrium, what is the density profile of the gas? How does it depend on the various interaction parameters? So we came up with a very nice field theoretic method of solving this problem, and which essentially gives us the exact density profile of this interacting gas for arbitrary interactions. Okay, and what we find is so there is the interaction strength. This interaction is of the form 1 over r to the power k, and what we found is as we change this parameter k, we can actually, the density profile undergoes like all sorts of forms, and undergoes a transition from a form with a peak at the center to a form which has peaks at the sides. Now this particular model actually, for different values of k, it captures lots of well-known models like the Coulomb gas, the log gas, which is related to random matrices, and also one component plasma. Okay, so this is a very general model, and so it's nice that we could get this very exact solution. So this work was published in PhysRev letters, and it's already quite well cited. So for this same class of model, another question we looked at is what is the looking at the density profile was looking at the mean properties of the system. Then we also looked at questions like fluctuations, and one sort of very interesting question is what is the fluctuation of the particle at the edge of the system. Okay, so this problem for the log gas is a very famous problem, and it was solved by these people called Tracy and Widom, and they found some universal distribution for this end particle statistics. So what we did in our project is to compute this this distribution for the case of this one component plasma. Okay, so and what we found is that it falls in a different universality class, and for this problem we could compute the full distribution, both the mean and also the large deviations. So this also required some highly non-trivial mathematical techniques which we invented for this particular model. So this is our main work on strongly correlated systems. The second set of works is on systems of particles which describe active matter. Okay, so active matter is at a microscopic level, the particles are sort of like Brownian particles, but then there's some extra ingredient in the which captures the fact that they are active. So basically, there's some inbuilt motion which is not thermal. So as a result, I mean, even solving like single particle problems is highly non-trivial. And so we studied a large number of different problems of single active particles in sort of traps. Okay, and for this in both 1 dimensions and 2 dimensions, and these are systems which have been realized experimentally, and what we could do is actually obtain a number of exact results for these systems. So and again we found like qualitatively very interesting properties of where the steady state distribution shows all kinds of non-trivial behavior as you change some parameters. We got some sort of a phase diagram where you see active and passive phases of these particles. And again we produced a number of papers. I mean, I think there are about 8 papers coming out in this area, and 2 of these papers are already have more than 100 citations. Okay, so because what we did was completely this exact results that we obtained really started a very new sort of field. So this is the second problem that we looked at. The third problem is related to anomalous heat transport in low dimensional systems. So what is known is that in 1 and 2 dimensional systems, there's this famous law, Fourier's law of heat conduction. So this law is not valid, and what one finds is that the thermal conductivity sort of becomes very large and in fact diverges for macroscopic systems. So we looked at a sort of simple but quite still non-trivial models, and we could show that the hydrodynamic description of these systems is described not by diffusion equation but by a fractional diffusion equation. Okay, so this we could derive in a very mathematical and rigorous way, and we did detailed comparisons with microscopic simulations, and we have sort of established that this is the right way to describe these anomalous systems, and so this resulted in 3 papers. And we also wrote a sort of a review article on this general area of fractional diffusion equations describing systems with anomalous transport. So in all we published I think around 11 papers, out of which there are 2 FISREV letters and several papers which are now highly cited. So I would say it's a very successful collaboration. Okay, so I think the way Cephipra really got in here was, of course, so this set of French collaborators, we had some collaborations, but I mean, this really helped us to meet more often, and I think this physical interactions between is really important. I mean, it speeds up collaborations, speeds up interactions by a huge amount, and both ideas get generated and also calculations get completed much faster. And so this is really important that physical interactions take place. So this is of course where CEFIPRA really helped most, I think, because we could travel to Paris. I mean, the CEFIPRA people could come to Bangalore. In fact, it also, we could, using the CEFIPRA budget, we could also attend a couple of conferences in Europe, and which were also very useful in also talking about our work. That was of course the most important aspect. Apart from that, I think using the CEFIPRA fellowship, we could support a couple of postdocs, both here and in France. And they also, of course, were very deeply involved in the projects. Then, of course, we could buy equipment like laptops and so on. I think, yeah, so the CEFIPRA contribution, of course, was really huge.
This episode is brought to you with the content support from CEFIPRA and the technical support from the Sparrows team. We extend our heartfelt thanks to the Director of CEFIPRA, Professor Nitin Seth and Dr. Payal, for their continuous guidance and support. Stay tuned for more episodes and thank you for joining.
आइए हम सुने विज्ञान की अनकही कहानियाँ। आइए हम सुने विज्ञान की अनसुनी